This Linux course covers a wide range of essential Linux topics, from beginner to advanced. The course also includes interactive labs to provide hands-on experience with the skills you'll learn. Linux specialist Aaron Lockhart created this course.
In this course, Aaron teaches you the basics of the Linux operating system, including how to log into a host through a local and remote console, how to read and use system documentation, how to work with files and directories, how to create and manage hard and soft symlinks, list, set, and change file permissions, search file with Grep, how to analyze text with regular expression, how to manage user accounts, and how to manage resources also, and then how to manage user access privileges as well as access to the root account, which is kind of the primary account of the system. This course is about 2 hours of video and 2 hours of hands-on lab time. By the end of this course, you should aim to get a high-level understanding of Linux and not just the theory, but also the experience with the hands-on practice. Now, each concept taught in this video is followed by a hands-on lab. Our labs open right up in your browser, and it comes absolutely free with this course. So there's no need to spend any time on setting up your own environments. You go from watching a video to practicing it in less than 30 seconds. The labs are challenge-based, and so each lab is specifically designed to help you practice the concepts that you just saw in the video. So here's how I recommend that you take this course. Set aside 4 hours of time for this entire video and course. Turn off the notifications on your mobile phone. Turn off any desktop notifications like Slack, email, Discord, or any other distractions, and just get into that focus zone. Make sure you are ready to block out a few hours of your time and aim to stick to the curriculum and labs in order to finish the course. So before we begin, head over to this link to download the deck with notes used in this course and to access the labs that come free with this course. Go to code.wiki, so kode.wiki//Linux-labs, or scan the QR code that you see on the screen. Once you are on the page, click on the button to enroll for free. The first topic has the deck with the resources that you can download, and this is handy to keep while you're working on the labs so that you can use it for reference. The remaining topics are the labs. So select a topic and click the start button, and that's going to load the lab in your browser. But you don't have to start them now. We'll let you know when to access which labs. So enroll in the labs, download the deck, and then come back here to continue the course.
Hello, and welcome to Code Cloud's Linux tutorial. I'm Aaron Lockhart, and I'll be your instructor for this course. As per Stack Overflow's insights, the most common and the most loved platform used for development work happens to be Linux. Here's what you'll learn in this course. Log into local and remote graphical and text mode consoles, read and use system documentation, create, delete, copy, and move files and directories, create and manage hard links and soft links, list, set, and change standard file permissions, use pagers and the BI editor, search files using Grep, analyze text using basic regular expressions and extended regular expressions, create, delete, and modify user accounts, local groups, and group memberships, configure user resource limits, manage user privileges, and how to manage access to the root account. This is primarily a hands-on course with interactive videos and labs that will help you learn Linux. Our crisp and concise lectures simplify complex concepts using illustrations and animations. Other concepts are explained by demonstration videos. These will be live demonstrations where I will walk you through a task or a concept with a video example. And of course, you have access to labs where you can get hands-on practice on everything we teach. Since you'll be learning to perform tasks a system administrator would normally perform, you'll need to get practice, so it's important that you spend time working with the labs for the course. Our hands-on labs open right in your browser, so you won't need to set anything up for yourself to practice. Each lab will have a series of questions or exercises and a terminal for you to perform the necessary tasks. There are also hints and solutions in case you get stuck, but always try to work out the solutions for yourself. You'll get instant feedback from the lab system when you check your answer, and you can work with the lab as many times as you want for each set of lessons until you're comfortable with performing the tasks before moving on to the next set of lessons. Well, I'm excited to get started. In this lecture, we'll talk about how to log into a Linux system locally and remotely in both graphical and text mode consoles. This will be a very practical course. We'll take a look at why we need to do certain things, then we'll explain how to do those things. We'll experiment with a few commands at the beginning of each lesson, then we'll explain the theory behind those commands. This should make the course more fun, engaging, and easier to understand. So let's dive right in and start with some simple concepts. We're all used to logging into apps or websites by providing a username and password. Logging into a Linux system is pretty much the same, so there's not much mystery here. We'll look at 4 ways to log in. Logging into a local Linux system using the local text mode console, logging into a local Linux system using the graphical mode console, logging into a remote Linux system using a text mode login, and logging into a remote Linux system using a graphical mode login. You'll often hear terms like console, virtual terminal, and terminal emulator. It may be hard to understand why they're called this way. Nowadays, a console is just a screen where your operating system displays some text and where it allows you to log in or type commands. And a terminal emulator is nothing more than a graphical app that runs in a window and does a similar thing. Shows you text output and allows you to type commands. These terms come from the old days of computing. Computers were incredibly expensive, so a building may have had a single one available for the entire building. But multiple people could connect to it and do their work by using physical devices that allowed them to type text and commands and also display on a screen what was currently happening. Those devices were consoles or terminals. So instead of buying 25 super expensive computers, you could have just one, but 25 people could use it, even at the same time. Nowadays, consoles and terminals in Linux are usually things that exist in software rather than hardware. For example, when you see Linux boot and a bunch of text appears on the screen telling you what's happening as the operating system is loading, that's the console. After a Linux machine has booted, if you press Ctrl-Alt-F2 on the keyboard, you'll see a virtual terminal, in this case, VT2. If you have Linux installed on your desktop with a graphical user interface, when you want to type commands, you open a terminal emulator. Let's move back to logins. In practice, most often, you'll log into remote Linux systems. But let's start with some less common scenarios. Local is just a tech word for something that is in front of you, or something you can physically access. A computer on your desk is a local. A server running on Google Cloud is remote. Usually, when Linux is installed on servers, it's installed without a GUI, no graphical user interface components. There's no mouse pointer, no buttons, no windows, no menus, nothing of that sort, just text. But you might sometimes run across servers that include this GUI. Logging in is super easy as it's all in your face. You'll see a list of users you can choose from, and you can then type your user's password. And don't forget to log out when you finished your work. If the device has the typical server-oriented Linux OS installed without any GUI components, logging in locally is also easy. You'll usually see something like this on your screen. There's no list of users this time, but you can just type your username and then your password. And note that you won't see your password as you type. When your work is done, you should type exit to log out. Again, most Linux operating systems running on servers will have no GUI components installed, but you'll sometimes run into exceptions. Connecting to a remote server that has a graphical user interface is slightly more tricky. First of all, there is no standard set in stone. Whoever configured that server chose their preferred way of dealing with these remote graphical logins. They could have chosen to install a VNC solution, that's virtual network computing. In this case, you'd need to download the proper VNC client, also called a VNC viewer, to connect to it. This might be tight VNC or real VNC or something else entirely. It all depends on the VNC server running on the remote system and which VNC clients your local operating system supports. If the administrator of that server wanted to let Windows users connect easily, it might mean that they use a solution allowing for RDP connections, or Remote Desktop Protocol. This means that you could just click on Windows Start button and type Remote Desktop Connection, open that app, and then enter the username and password you've been provided. Whatever it might be, connecting to a remote graphical console is pretty easy. It all boils down to downloading the application that lets you do that, entering the remote system's IP address, followed by a username and a password. Initiating a text-based remote connection to a Linux system is pretty standard. That's because almost every Linux server uses the same tool that allows for remote logins, the OpenSSH daemon. That's a program that runs in the background on the server all the time. SSH comes from Secure Shell. Until SSH, something called Telnet was the standard. Telnet was highly insecure as it did not encrypt communication between you and the server you were connecting to. So this meant that anyone on the same network with you could steal your Linux user password and see everything you did on that server during your Telnet session. The SSH protocol uses strong encryption to avoid this, and the OpenSSH daemon is built very carefully to avoid security bugs as much as possible. Long story short, OpenSSH is used by millions of servers and has stood the test of time, proving to be very hard to hack. For these reasons, everybody happily uses it and trusts that it can do a pretty good job at only letting authorized people log into their operating systems while keeping bad people out. In case you're following along on your virtual machine, log in locally, directly from the virtual machine window, and then enter this command. That's IP space A. You'll see which IP your machine uses. I've outlined the information we're looking for in yellow. We'll use this IP, in our case, 192.168.0.17, to simulate a situation where we have a server in a remote location. Now to recap, we have an SSH daemon program running on the server. This listens for any incoming connections. To be able to connect to this remote SSH daemon, we'll need something called an SSH client, yet another program. This client will run on our current laptop or desktop computer. macOS systems and Linux-based operating systems such as Ubuntu already have an SSH client pre-installed. If you're on macOS or Linux, open a terminal emulator window. In the past, if you were running Windows, you needed to install an SSH client like PuTTY. On the latest Windows 10, this is no longer necessary, as an SSH client is also pre-installed. If you're on Windows, click the Start menu and type CMD to open up Command Prompt. To connect to a remote Linux system through SSH, type SSH space, the username you would like to use on the remote Linux system, an @ symbol, and then the IP address of the machine. Here we have Aaron at 192.168.0.17. Of course, replace Aaron with the actual username you created inside your Linux OS running in the virtual machine, and do the same with the IP address. From here on, we'll stay inside this SSH session to go through all the exercises in the upcoming lessons. Here we're going to demonstrate a graphical login for a local machine. We're going to demonstrate a remote login using RDP on a remote machine graphically, and we'll also demonstrate a text mode login via SSH. So to get started, we have a CentOS VM here, already booted up. So we have the graphical package installed, and we'll select our username. It's going to be a pretty familiar process, the same one that you use at home or on your work computer. You'll provide your username. After selecting that, you'll provide your password and click Sign In. After a moment, it'll load the default operating environment, which for CentOS is going to be GNOME. So we can go ahead and log out of that particular session. Next up, I've configured another VM to accept Windows Remote Desktop connections. So you open your Remote Desktop tool, provide the IP address, which you already have filled in here, and click Connect. That loads a little bit different login screen. It's already pre-populated the username because I've used this before. That username is student. So we'll provide the password here. And click OK. And that's going to load a remote graphical session using that Windows Remote Desktop tool. You can see the IP address of the machine at the top. And while we're here, I'm going to go over to Activities and select the GNOME terminal to open a terminal emulator. And here we can see that we are student at lfcs-centos2. This is a host name. So here we'll type SSH. We're going to do Aaron at 192.168.0.17, which is the IP address for the first client that we logged into using the local login. It's going to prompt us for the password, which, as you'll recall from the lecture video, is not going to show anything when we type. Go ahead and hit enter, and now we can see our last login. And we'll see that we are Aaron at lfcs-centos, which was the first host. You can go ahead and exit to end your SSH session. Now you see that we're back as student at lfcs-centos2. We can type exit to close the terminal emulator, and then we'll go over and log out. There will be many commands we will use in Linux, and each command has a lot of command line switches. How are we supposed to remember them all? As we use a command repeatedly, we'll learn everything about it and memorize what each option does. But in the beginning, we might forget about these options after just one or two uses. That's why Linux gives you multiple ways to access help manuals and documentation right at the command line. Let's say you want to see that long listing format with ls to get a good look at file permissions, but you forgot what the correct option was. Was it -p for permissions? We can get a quick reminder with ls-help. This will show us a lot of output, but if we scroll up, we'll find what we're looking for, the -l flag in this case. You can see how command line options are sorted alphabetically and described with short text. That's why the --help option for commands will very often be helpful when we forget about these options. And we will, as there are so many of them for each command. --help will usually show a condensed form of help with very short explanations. For ls, that's okay, as it's a very simple command. Other commands, however, are very complex, and we need to read longer explanations to understand what they do and how we use them. So let's take journalctl as an example. It's a command that lets us read system logs. Journalctl --help will show us this. Notice that this opens in a slightly different way. You can take a look at the bottom left corner and you'll see lines 1 through 27. This opened in what Linux calls a pager. It's simply a text viewer of sorts that lets us scroll up and down with our arrow keys or page up and page down, and to exit this help page, we press Q. All important commands in Linux have their own manuals or man pages. To access a command's manual, enter man followed by the name of the command. In our case, we'd use man journalctl. So now we get a short description of what the command does in the name section, a general syntax for the command in the synopsis section, a detailed description of the command, how it works, and so on in the description section. There could be a detailed description of command line options in the options section, and some manual pages even have some examples near the end of the manual. Sometimes you'll have two manual pages with the same name. An example is printf. Printf is a command, but printf is also a function that can be used by programmers. Manual pages can fall into one of these categories or sections, and we can see these by looking at the man page for man itself by typing man. If you want to read the man page about printf the command, you tell man that you want to consult printf from section 1, like this, man1 printf. If you want to read about printf the function, you tell man that you want to look at section 3, man3 printf. It's useful to know that during online exams, the Linux Foundation will let you use man and -- help. Try to use help if you forgot a command line option, as that gives you the fastest results. Diving deep into a manual page will eat up more time. But this is all well and good when we know what command we want to explore. But what if we can't even remember the name of the command that we need to use? Imagine you forgot the name of the command that lets you create a new directory. How would you search for it? Apropos is a command that lets you search through man pages. It looks at the short descriptions of each man page and tries to see if it matches the text we entered. For example, with this line, we can search for all man pages that have the word director in their short descriptions. We'll use director and not directory. Director will match commands that contain the word directory, but also ones that contain directories. So we keep it more generic this way. The first time we run apropos director, we'll get an error. That's because apropos relies on a database. A program must refresh it periodically. Since we just started this virtual machine, the database hasn't been created yet. We can create it manually with sudo mandb. On servers that have already run for days, there should be no need to do this, as it will be done automatically. Now the apropos command should work. If we scroll up, we can see the entry that we're looking for, which is mkdir. But those are a lot of entries. It makes it hard to spot what we're looking for. You see, apropos doesn't just list commands. It also lists some other things we don't need currently. We see stuff like the to in parenthesis. That signals that the entry is in section 2 of the manual pages. That's system calls provided by the Linux kernel. That's just too advanced for our purposes. Commands will be found in sections 1 and 8. And we can tell apropos to only filter out results that lead to commands from these sections. We do this by using the -s option, followed by a list of the sections we need, such as apropos -s 1,8 director, and we can spot what we're looking for more easily. So notice how mkdir's description contains the word directories. If we'd used the word directory in our apropos search, this command wouldn't have appeared, since directory wouldn't have matched directories. This is something to keep in mind when you want to make your searches as open as possible and match more stuff. Another thing that'll save you a lot of time is auto-completion. For example, type system C and then press tab. That'll give you systemctl. Although this is not technically system documentation, it can still be helpful. Many commands have suggestions on what you can type next. For example, try this. Type systemctl, add a space after the command, but don't press enter, and now press tab twice. You'll get a huge list of suggestions. This can help you figure out what your options for that command are. Although you should not always rely on it. It's not necessary that absolutely all options are included in this suggestion list. So let's do a little more. Add to that list-dep and then press tab. You'll see that indencies will get added to the end, and you get systemctl list-dependencies. This is tab auto-completion, and many commands support it. When you press tab once, if your command interpreter can figure out what you want to do, it will automatically fill in the letters. If there are many autocomplete options and it can't figure out which one you want, press tab again and it will show the list of suggestions we observed earlier. These will be huge time savers in the long run, and they might even help you in the exam to shave off a few seconds here and there, which might add up and let you explore an extra question or two. Tab suggestions and auto-completions also work for file names or directory names. So for example, try typing ls/u and then hitting tab. That'll give you /usr/. Now, if you do it again, so press tab 2 more times, you can see the directories available in /usr/ without even needing to explore this directory with ls beforehand. And if we had a long file name like wordpress_archive.tgz, We might be able to just type WOR, press tab, and that long name will be auto-completed. So here's a recommendation. While manuals and -- help pages are super helpful, the first few times you use them, it might be hard to figure out how to do something with that info alone. We recommend you take a command you know nothing about and try to figure out with just man and -- help how to do something with it. This practice will help you develop the ability to quickly look for help when you're taking the LFCS exam. There will be questions about theory that you either don't know about or you just forgot. If you know how to quickly figure out the answer with a man page or -- help, you'll be able to pass the exam much more easily.
It's time to gain hands-on experience with the Code Cloud Labs. This course is designed for you to have a seamless experience from start to finish. And that's why we have labs after each concept that will help you gain hands-on experience on exactly what you learned up until that moment. So to begin with, we're going to work on an existing Linux host that's already set up. And this will help you get familiarized with the Linux operating system, the Linux command line interface, and it will get your hands dirty, to borrow a phrase. At the end of this course, we'll share instructions on setting up your own local environment for you to continue your studies. We do not want you to be distracted with any issues that might come up when you try to build your own Linux system or Linux cluster. So my recommendation is to aim to complete this course only using the labs that we provide in the browser and go from start to finish without any interruption. If this is a 2-hour course, then you should aim to complete it in 2 or 4 hours at the maximum. So head over to the labs using the links given below and come back here once you are done.
Now we'll look at how to create, delete, copy, and move files and directories in Linux. Before we dive into this lesson, we need to understand a few basic things. What is a file system tree? What is an absolute path? And what is a relative path? To list files and directories in your current or working directory, we use the ls command in Linux. Using ls in your home directory might look like this. ls comes from list. On Linux, files and directories can have a name that begins with a dot. An example would be the .ssh directory. These won't be displayed by a simple ls command. They are, in a way, hidden. To list all files and directories, even the ones beginning with a dot, use ls-a. The -a flag comes from the word all. Of course, to list files and directories from a different location, we just type the directory path at the end of ls, like ls/var/log or ls-l/var/log, to list files and directories in a different format called a long listing format. That's going to show us more details for each entry, like the permissions for a file or directory, what user or group owns each entry, and when it was last modified. We can combine the -a and -l command line options like this, either by writing ls-a-l or ls-al. This will display entries in the long listing format and also show us the pseudo-hidden files and directories, which have a name beginning with a dot. It doesn't matter which order you put the flags, and you don't have to put a dash in front of each of them. However, the last form is preferred as it's faster to write. There's also a command line option -h that shows sizes in human readable format like bytes, kilobytes, megabytes, and so on. And this has to be combined with the -l option. If we wanted to use all three options, we could use ls-alh, and there we can see all of our previous information, but also the human readable sizes like bytes, kilobytes, and megabytes. Linux organizes files and directories in what it calls the file system tree. Why is it called a file system tree? Well, that's because, like a tree we'd see in nature, this also has a root, branches, and leaves. Except Linux's file system tree is inverted. The root is at the top, and its branches and leaves grow downward. The root directory is /, and this is the top level directory. There can be no other directories above it. Under /, there are a few subdirectories like home, var, etc, and so on. These subdirectories may also contain other subdirectories themselves. To access a file or directory on our command line, we must specify its file path or directory path. This path can be written in two different ways. The easiest to understand is the absolute path. /home/aaron/document/invoice.pdf is an example of such a path. Absolute paths always start out with the root directory represented by /. Then we specify the subdirectories we want to descend into. In this case, first home, then Aaron, then documents. And we can see the subdirectory names are represented by a /. Finally, we get to the file we want to access, which is invoice.pdf. An absolute path can end with the name of a file, but also with the name of a directory. If we'd want to refer to the documents directory, we could specify a path like /home/aaron/documents. To understand a relative path, we must first explore what the current directory means. This is also called the working directory. To see our current or working directory, we can type pwd, and that stands for print working directory. When we're working at the command line, we're always inside of a directory. For example, if we log in as user Aaron on some server, our starting directory might be /home/Aaron. And every user starts in its home directory, so Jane might have it at /home/Jane, and root, the super user or administrator, has it at /root. To change our current directory, we use the cd command, and cd stands for change directory. So if we entered cd/var/log, that would change our current directory to /var/log. And here we used an absolute path. But we can also change directories in another way. For example, using cd ... which would take us one directory up. So if we were to cd first into /home/Aaron, running cd ... would take us into /home, which becomes the new current directory. ... always refers to the parent directory of our current directory. So this was a pretty simple example of using a relative path, so let's dive a little deeper. Let's imagine our current directory is /home/Aaron. With relative paths, we can refer to other places in one of three main ways. The first is locations under our current directory. So for example, documents/invoice.pdf. Since we're in /home/Aaron, typing a path like documents/invoice.pdf is like typing /home/Aaron/documents/invoice.pdf. Our relative path gets added to the current directory, and we get our PDF file. We can also refer to locations in our current directory. So typing invoice.pdf will access the file at /home/Aaron/invoice.pdf. We can also refer to locations that are above our current directory. Typing /invoice.pdf points to the file at /home/invoice.pdf. Since we used .. we basically said, go one directory up. And we can use .. multiple times. .. /invoice.pdf points to the file at /invoice.pdf. The first .. moved the relative path to home, and the next moved it to /. So a few extra tips. If you're in /var/log currently, and you want to move to /, you could run the command cd/, and it will take you to the root directory. You can return to your previous working directory with the cd- or cd- command. That would take you back to /var/log. So if you're in the /var/log directory, and you want to return to your home directory, which in our case is /home/Aaron, you'd just use cd by itself. CD without any options or paths after it will always take you back to your home directory. So let's assume we're in our home directory and we want to create a new file. To do this, we use touch. For example, to create a file named receipt.pdf, we would type touch receipt.pdf. And this will create it inside the current directory. To create it at another location, we could use touch/home/jane/receipt.pdf. And since we're in /home/Aaron, we could also use the relative path to create the file in /home/Jane by typing touch./Jane/receipt.pdf. Both commands would work the same because all the commands we'll discuss accept both absolute and relative paths, so we won't mention these alternatives for each one. Just know that after the command, you can use any kind of path you want. To create a new directory, use mkdir. For example, mkdir receipts. mkdir comes from make directory. To copy a file, we use the cp command, which is short for copy. cp is followed by the path to the file we want to copy, which is our source, and then the path to the destination where we want to copy it. To copy receipt.pdf to the receipts directory, we'd use cp receipt.pdf receipts/. Notice how we terminated the path to the receipts directory with a slash to make it receipts/. Without the slash, it would have worked too. But it's good practice to end your directories with a slash. This way, you'll form a healthy habit and get a visual indicator that tells you when receipts without a slash might be a file and receipts with a slash might be a directory. To copy receipt.pdf to the receipts directory, but also choose a new name for it, we could use cp receipt.pdf receipts/receiptcopy.pdf. To copy a directory and all its contents to another directory, run the cp command as before, but with the -r option. The -r is a command line option. They're also called command line flags, and that tells cp to copy recursively. And that means to copy the directory itself, but also descend into the directory and copy everything else it contains, like files, other subdirectories it may have, and so on. So for example, say I have a lot of directories, subdirectories, and files under the receipts directory. I'd like to back up all the contents into a backup directory named backup of receipts. To do this, we'd run the command cp-r receipts/backup of receipts/. This copies all subdirectories and files from the receipts folder into the backup of receipts folder. The name you choose for your clone directory must not exist at your destination. So, for example, if we already had a directory at /home/Aaron/backup of receipts, then this will just move receipts there, and it would end up at documents/backup of receipts/receipts/. So we saw that the copy operation copies a file from one place to another, resulting in two copies of the files, the original one and the one in the new location. But what if we want to move a file from one location to another, so that the file is not present in the original location and is only present in the new location? For this, use the mv command. mv stands for move. Run the command mv receipt.pdf receipt/ to move the file from receipt.pdf to the receipts folder. The file is moved and there is only one copy of the file available. To rename a file, we can use mv receipt.pdf old receipt.pdf. And to rename a directory, we can use the new name as the destination, such as mv receipts/old receipts/. Notice here that you don't need to use the -r recursive flag when you use mv. MV takes care of all of that itself. To delete a file, we use the rm command. Rm comes from remove. To delete the file invoice.pdf, we can use rm invoice.pdf. To delete a directory, like the invoices directory, we'd use rm-r invoices/ to make it recursive. So once again, the -r option makes it recursive, deleting the directory along with its subdirectories and files. So whenever you copy or delete directories, remember to always add the -r option. In this lecture, we'll look at how Linux manages hard links. To understand hard links and soft links, we must first learn some very basic things about file systems. So let's imagine a Linux computer is shared between two users, Aaron and Jane. Aaron logs in with his own username and password, and Jane logs in with her own username and password. This lets them use the same computer, but have different desktops, different program settings, and so on. So Aaron takes a picture of the family dog and saves it to /home/Aaron/pictures/family_dog.jpg. Let's simulate a file like this. With this, we created a file at pictures/family_dog.jpg and stored the text picture of Milo the dog inside. There's a command on Linux that lets us see some interesting things about files and directories. That's the stat command. So here we'll notice an inode number. Well, what is this? File systems like XFS, ext4, and others keep track of data with the help of inodes. Our picture might have blocks of data scattered all over the disk, but the inode remembers where all the pieces are stored. It also keeps track of metadata, things like permissions, when the data was last modified or last accessed, and so on. But it'd be pretty inconvenient to tell your computer, hey, show me inode 529.46177. So we work with files instead, the one called family_dog.jpg in this case. The file points to the inode, and the inode points to all the blocks of data that we require. And finally, we're going to get to what interests us here. We notice this in the output of our stat command. There's already one link to our inode. Yes, there is. When we create a file, something like this happens. We tell Linux, hey, save this data under this file name, family_dog.jpg. And Linux says, okay, we'll group all this file's data under inode 529.46177. Data blocks in inode are created. We'll hard link the file family_dog.jpg to inode 529.46177. So now when we want to read the file, we say, hey, Linux, give me the data for family_dog.jpg. And Linux says, okay, let me see where that inode links to. Here's all the data you requested for inode 529.46177. So the number shown as links in the output of the stat command is the number of hard links to this inode from files or file names. It's pretty easy to understand, but why would we need more than one hard link for this data? Well, Jane has her own folder of pictures at /home/Jane/pictures. How could Aaron share this picture with Jane? The easy answer is to just copy /home/Aaron/pictures/family_dog.jpg to /home/Jane/pictures/family_dog.jpg. No problem, right? But now imagine we must do this for 5,000 pictures. We would have to store 20 gigs of data twice. So why use 40 gigs of data when we could just use 20? How can we do that? So instead of copying /home/Aaron/pictures/family_dog.jpg to /home/Jane/pictures/family_dog.jpg, we could hard link it to /home/Jane/pictures/family_dog.jpg. And the syntax of the command to do that is like this. Ln path to the target, path to the link file. The target file is the file you want to link with, and the link file is simply the name of this new hard link we create. Technically, the hard link created at the destination is a file like any other. The only special thing about it is that instead of pointing to a new inode, it points to the same inode as the target file. In our imaginary scenario, we'd use a command like ln/home/aaron/pictures/family_dog.jpg /home/jane/pictures/family_dog.jpg. Now our picture's only stored once, but the same data can be accessed at different locations through different file names. And if we were to run the stat command now, we'd see the links are now 2, as the inode now has 2 hard links pointing to it. And another beautiful thing about hard links is this. Say Aaron and Jane share the same 5,000 pictures through hard links, and maybe Aaron decides to delete his hard link of /home/aaron/pictures/family_dog.jpg. What will happen to Jane's picture? Nothing. She'll still have access to that data. But why? Because the inode still has 1 hard link to it. Before it had 2, now it has 1. But if Jane also decides to delete her hard link to the picture at /home/jane/pictures/family_dog.jpg, the inode will have 0 links to it. And when there are 0 links, the data itself will be erased from the disk. The beauty of this approach is that people that share hard links can freely delete what they want without having a negative impact on other users that still need that data. But once everyone deletes their hard links to that data, the data itself will be erased. So data is intelligently removed only when everyone involved decides they don't need it anymore. There are some limitations for hard links in Linux. You can only hard link to files and not to directories. You can also only hard link to files on the same file system. If you had an external drive mounted at /mnt/backups, for example, you would not be able to hard link a file from your SSD at /home/aaron to some other file on /mnt/backups, since that's a different file system. There are some other things to take into consideration when you hard link. First, make sure that you have the proper permissions to create the link file at the destination. In our case, we need write permissions at /home/jane/pictures. And second, when you hard link a file, make sure that all users involved have the required permissions to access that file. For Aaron and Jane, this might mean that we might have to add both their usernames to the same group. For example, family. Then we'd use a command to let the group called family read and write to this file. You only need to change permissions on one of the hard links, and that's because you're actually changing permissions stored by the inode. So once you change permissions at /home/aaron/pictures/family_dog.jpg, /home/jane/pictures/family_dog.jpg, and all other hard links will show the same new sets of permissions. Let's look now at how Linux manages soft links. You know how when you install a program on Windows, you might get a shortcut on your desktop? You double-click on that shortcut and the application gets launched. Well, the application is obviously not installed on your desktop. It may have its files stored in the C:/program files/mycoolapp directory. And when you double-click on the shortcut, this only points to an executable file at C:/program files/mycoolapp/application.exe. So the double click on that shortcut basically redirects you to the file C:/program files/mycoolapp/application.exe, which then gets executed. Soft links in Linux are very similar. A hard link pointed to an inode, but a soft link is nothing more than a file that points to a path instead. It's almost like a text file with a path to a file or directory inside. The syntax of the command to create a soft link, which is also known as a symbolic link, is the same as before, but we add the -s or -- symbolic option. So it looks something like this. ln-s, path to the target file, followed by the path to the link file, where the path to the target is the file or directory that our soft link is going to point to, and the path to the link file is where our soft link will actually be created. So, for example, to create a symbolic link that points to the /home/aaron/pictures/family_dog.jpg file, we can run the following command. It's ln-s/home/aaron/pictures/family_dog.jpg family_dog_shortcut.jpg. Now, if we list the files and directories in long listing format with the ls-l command, we'll see output like this. And the L at the beginning shows us that this is a soft link. And ls-l even displays the path that the soft link points to. But if this path is long, ls-l might not show the entire path. An alternative command to see the path stored in a soft link is readlink, followed by the path to the soft link. So in our case, that would be readlink family_dog_shortcut.jpg. You may also notice that all the permission bits, R, W, X, read, write, and execute, seem to be enabled for this file. And that's because the permissions of a soft link do not matter. If you were to try to write to a file like fstab_shortcut, and this would be denied because the permissions of the destination file apply, and /etc/fstab does not allow regular users to write here. So in our first command, we used an absolute path. That was /home/aaron/pictures/family_dog.jpg. If we ever change the directory name Aaron in the future to something else, this soft link will break. You can see broken links highlighted in red in the output of the ls-l command. To tackle this, you could create a soft link with a relative path. Say, for example, you were in the home directory of Aaron, you could create a soft link using the relative path of the family_dog file instead of specifying the complete path. So that way, when someone tries to read relative_picture_shortcut, they would get directed to pictures/family_dog.jpg relative to the directory where the soft link is. Since soft links are nothing more than paths pointing to a file, you can also soft link to directories. So something like ln-s pictures/ followed by a shortcut to the directory would be valid. And you can also soft link to files or directories on a different file system, which differs from the way that Linux handles hard links.
So head over to the labs using the links given below and come back here once you are done.
We'll now discuss how to list, set, and change standard file permissions in Linux. To understand how file and directory permissions work on Linux, we must first look at file and directory owners. If we type ls-l, we'll see something like this. Any file or directory is owned by a user. In this case, we see that the file family_dog.jpg is owned by the user called Aaron. Only the owner of a file or directory can change permissions, in this case, Aaron. The only exception is the root user, that's the super user or administrator account, which can change permissions of any file or directory. In the second field, we see that this file also has a group associated with it, and that's the family group. We'll see later what the role of groups are. To change the group of a file or directory, we use the chgrp command, and that stands for change group. And its syntax is chgrp, followed by the group name, followed by the file or directory name. So, for example, to change this file's group to wheel, we'd use chgrp wheel family_dog.jpg. If we do another ls-l, we can see that the group has now changed to wheel. We can only change to groups that our user is a part of, and to see which groups our current user belongs to, we can use the groups command. So this means we could change the group of our file to Aaron wheel, or family. There's also a command to change the user owner of a file or directory, and that's CHOWN or chown. That stands for change owner. And its syntax is chown followed by the user that we'd like to change it to and the file or directory's name. So, for example, to change ownership of this file to Jane, we'd use chown Jane family _dog.jpg, but only the root user can change the user owner, so we'd have to use the sudo command to temporarily get root privileges, and that's why here we have sudo chown Jane family _dog.jpg. So with another ls-l, we can see the user has now changed to Jane. We can change both the user owner and the group with a different syntax of chown. That'd be chown user :group followed by the name of the file or directory. And again, since only root can change user ownership, we're going to set the user back to Aaron and the group to family to revert all of our changes by using sudo chown Aaron family _dog.jpg. And one last ls-l will show us that the owner is Aaron again and the group is family. Our ls-l command also shows us the permissions of all files and directories in our current directory. The first character on that line shows us what type of an entry this is, so whether it's a file, a special file, a directory, and so on. So for example, we'd see D for a directory, L for a soft link, or dash for a regular file. And here's a table that shows the different identifiers and what they stand for. And we'll learn about some of these file types later in this course. The next 9 characters show us permissions. So the first 3 are permissions for the user that owns the file. The next 3 are permissions for the group that the file belongs to. And the last 3 are permissions for other users. That's any user that is not Aaron or not part of the family group in the example we've been working with. So let's see what R, W, and X mean in 2 different contexts, because they act in a certain way for files and have a slightly different behavior for directories. So here for a file, R means that the user, group, or other users can read the contents of this file. A dash means they cannot read it. W means the user, group, or other users can write to this file to modify its contents. And X means the user, group, or other users can execute this file. Some files can be programs or shell scripts, lists of instructions we can execute. So to be able to run this program or shell script, we must have the X permission. A dash permission here means the program or shell script cannot be executed. For directories, we must think a little differently. Unlike a file that may contain text to be read, executed, and modified, directories do not have such contents. Their contents are the files and subdirectories they hold. So read, write, and execute refers to these files and subdirectories they have inside. So R means the user, group, or other users can read the contents of this directory. We need an R permission to be able to run a command like ls-pictures/ and view what files and subdirectories we have in the directory. W means the user, group, or other users can write to this directory. We need W to be able to create or delete entries in that directory, like adding or deleting files or subdirectories, as when we use the mkdir command. And X means we can execute into this directory. We need X to be able to do cd pictures and enter into the pictures directory. When directories are meant to be accessible, you'll normally find both the R and the X permissions enabled. Whenever you're on a Linux system, you're logged in as a particular user. We've changed permissions in an interesting way to make this easier to understand. So look at the permissions for the family _dog.jpg file. It's set to -r -rw -. That's read only for the owner, read-write for the group, and no permissions for others. We see that the current owner of the file is Aaron, and we know Aaron is part of the family group. Can Aaron write to this file considering the fact that the owner has read-only permissions? It might seem that he should be able to do that as he's part of the family group and that group has read-write permissions. But if we try to add a line of text to this file, it fails. And why is that? Because permissions are evaluated in a linear fashion from left to right. With these permissions in mind, let's see how the operating system decides if you're allowed to do something. It goes through a logic like this. Who's trying to access the file? Well, that's Aaron. And who owns this file? Aaron is the owner. And owner permissions apply. Aaron can read the file, but cannot write to it. So write permission is denied. It does not evaluate the permissions of the group because it already matched you to the first set of permissions, the ones for the owner of the file. If you're logged in as a different user, for example, Jane, the logic would be more like this. So who's trying to access the file? Jane. And who owns the file? Aaron. Okay, owner permissions do not apply. Moving on to group permissions. Is Jane in the family group? Well, yes, she is. Okay, so group permissions apply. Jane has read-write permissions, so she can read and write to the file. If the user trying to access the file is not the owner and is also not in the family group, the last three permissions would apply, the permissions for other users. So now that we have a basic understanding of permissions, let's move on to how we can change them to suit our needs. To change permissions, we use the chmod command. And the basic syntax of the chmod command is chmod, followed by the list of permissions that we want to change, and then the name of the file or directory we're changing permissions for. We can specify these permissions in many ways, so let's start out with some simple examples. We saw that our owner, Aaron, cannot write to this file. So let's fix that. To specify what permissions we want to add on top of the existing ones, we use this syntax. To add permissions for the user or owner, it's u plus a list of permissions. So some examples would be u plus w, u plus rw, or u plus rwx. To add permissions for the group, it would be g plus the list of permissions. And to add permissions for other users, it would be o plus a list of permissions. In our case, we want to add the right permission for our user owner of the file. So here we would use chmod u plus w family underscore dog.jpg. Now the old r dash dash becomes rw dash with the newly added w permission. So we fixed our problem, and Aaron can write to this file. To remove permissions for the user owner, we would use u followed by a list of permissions. So some examples would be u-w or u-rw or u-wx. To remove permissions for the group, it would be g-list of permissions. And to remove permissions for other users, be o-the list of permissions. So at this point, we have the permission r-dash for other users. That means anyone on this system can read our family underscore dog.jpg file. If we want only the user owner and group to be able to read it, but hide it from everyone else, we can remove this R permission with chmod o-r family underscore dog.jpg. Now only Aaron or the family group can read this file, and no one else. With plus and minus, we saw that we can add permissions on top of the pre-existing ones or remove some of them from pre-existing ones. So if a file has rwx and we remove x, we end up with rw-. If another file has r-x and we remove x, we end up with r-. If we only care about removing the execute permission and we don't care what the other permissions are, this is perfect. but sometimes we'll have a different requirement. We'll want to make sure that permissions are set exactly to certain values, and we can do this with the equals sign. And just like before, this is done with the format U equals followed by a list of permissions, or G equals followed by the list, or O equals followed by the list. An example, we want to make sure that the group can only read this file but not write to it or execute it. To do that, we can run chmod g equals r family_dog.jpg. We can see that before group permissions were rw-, we didn't tell chmod to actually remove the w permissions, but by saying g equals r, we told it to make the group permissions exactly r-. This only affects the group permissions and not the user or other permissions. If we'd want to let the group read and write but not execute, we could use chmod g equals rw family_dog.jpg. We can see that whatever letter is missing will make chmod disable permissions for that thing. No X here means no execute permission will be present on the file. Which leads us to the next thing. What if we omit all of the letters? No R, no W, no X. Just chmod g equals family_dog.jpg. This is like saying make group permissions all empty. Another command that does the same thing would be chmod g-rwx family_dog.jpg. And that's going to do the same thing, but following a bit different logic that will remove all the permissions from the group R, W, and X. So we saw how to add permissions with plus, remove with minus, and set exactly to with equals. We can group all of these specifications in one single command by separating our permissions for the user, group, and others with a comma. For example, let's consider this scenario. We want the user to be able to read and write to the file and don't care if execute permission is on or off. We want the group to only be able to read exactly this permission, and we want others to have no permissions at all. Our command could be chmod u plus rw, g equals r, o equals family_dog.jpg. Or let's say we want the user to only be able to read and write, but we want to remove the write permissions for the group and leave all other group permissions as they were, and we don't care about permissions that apply to other users. We could use chmod u equals rw, g-w family_dog.jpg. Chmod supports another way to set and modify permissions, and that's through octal values. First, let's look at another command that shows us permissions, and that's the stat command. So we could do stat family_dog.jpg. And here's the list of permissions displayed by stat. We can see that rw-r-, has an octal value of 640. You can ignore the first 0 because that's for special permissions like set UID, set GID, and the sticky bit. And if we break this down, 640 means the user owner permissions are 6, the group permissions are 4, and the other permissions are 0. But how are these calculated? Let's take a closer look at this permission. We have RW for user, R for group, and none set for others. Each permission is represented in binary. If it's set, the binary is set to 1, or else it's set to 0. In this case, the first part is 110, the second part is 100, and the third part is 0. Converting this binary to decimal would give us 6 for the first part, 4 for the second part, and 0 for the third part. And here's a quick binary table for your reference. Let's take another example. this time RWX, R-X, and R-X. So the binary format would be 111, 101, 101, the decimal of which is 755. In the last example, it's read, write, and execute for all. So it's 1 for all of the bits, so the decimal value is 777. If you find binary difficult, another approach would be to use the octal table, and it's much simpler. For each permission, assign an octal value. For example, 4 for read, 2 for write, and 1 for execute. Then, whichever permission is set, consider the respective value for that, and for the permission bit not set, consider it to be 0. Once done, add up the numbers within each group. So you would get 4 plus 2 equals 6, 4 plus 0 is 4, and the last group is 0. Let's look at using the same approach for the other examples as well. So RWX, R-X, and R-X gives us 755. And full permissions give us 777. Once we identify the number we want to set it to, we can use the same in the chmod command as well. Instead of specifying the permissions for each group, we could just provide a number like this: chmod 640 family_dog.jpg.
So head over to the labs using the links given below and come back here once you are done.
In this demo, we'll be showing off pagers and the Vim text editor. Pagers are programs that allow you to open multiple pages of text and navigate through them while on the terminal. And the two pagers that we'll be looking at are called less and more. The first one we'll look at is less. It's a bit more feature rich than more. And to access it, you first type its name, followed by the name of the file that you want to open. In this case, I'm going to use the log file for the DNF package manager because that has enough information in it to really show off our pagers. So that's located at this location. We press enter. So now we've opened in the pager. And one of the ways you can tell that you're in a pager, because other programs might open them for you, is that in the bottom left corner, you'll see the name of the file highlighted there. So with the less pager, you can use the arrow keys up and down to move up and down in the file. And you can also have things like search functions. So for example, to search for text, you press the slash key, and you'll see that down in the bottom left-hand corner, followed by the term you'd like to search for. I'll search for debug, since I know that appears several times in this file. So you'll see on the first line here, it's been highlighted where it occurs. And to get to the next instance on a line where it would occur, you would press the N key. And that will continue to move to each new instance of debug. But you'll notice that it's skipping some of them. And that's because the case is sensitive. So to make it case insensitive, you need to pass the dash I option to ignore case. And that will start getting all of the instances of debug. And to move backward through previous results, you would hold the Shift key and press N. So a capital N will move upward through the previous results. And lastly, for less, in order to exit the pager, you press Q to quit. That's a brief overview of the less pager. More does not have as many features, but you do access it the same way. And you'll know you're in more because it will let you know down at the bottom. It will say more and show you a percentage. And for more, you move through things by pressing the space bar, and that moves a page at a time. And to get out of more, you press the Q key. So that is it for pagers. Let me clear my screen for you. Now we'll move on to the Vim text editor, that is VI improved. When you open it with Vim. It'll give you this nice little greeting screen with your blank file and a couple of things that you can do. It shows you a few of the commands that you can have. Vim is mode sensitive, so it has different modes to be in, and different keys and functions are available depending on the mode that you are in. In order to write text into a file, you need to press the I key. That's for insert. And you'll notice down at the bottom left-hand corner, it now says insert, and you can start typing text. Right, so we have this is our text for our Vim demo. I'll give a couple of blank lines here. All right, so some things that you can do with Vim. You press escape to go back to its default mode, and you can't type anything in the default mode. So for Vim, to search, you can use the / key, just like you did in less when you're in the default mode. So I'll search for this, and it doesn't find that because it is case sensitive. So I can search for one that we can find. So it'll highlight all instances of IS if I type is. If you want it to be case insensitive, you can do this, followed by an escape character, so that's a / going the other way, and then the letter C, lowercase letter C. Think of C for case. So that'll make it case insensitive. Okay. The next thing we would want to look at, in the default mode, you can go to a particular line number by typing a colon followed by the line number. So I've got about 3 lines in here. So to go to line 3, we'll take our cursor to line 3. I type 2. You can see we've gone back up to 2. And of course, 1 will take us back to the original line number. Right? And to copy a line of text, an entire line of text, when you're in command mode, you hit the Y key 2 times. Okay, so we've copied it. And then to paste that line of text, you can use the P key in command mode. So it'll paste it wherever you have it. You can also cut a line of text by using the D key 2 times. So DD will cut it. And you can also paste things that you have cut with the P key. So if you need to replace a line, go to a particular line and replace it. When you're working with a file, those are some useful Vim commands. Now, probably the most complicated thing about Vim the first time you open it is, how do you get out of it? A lot of people have trouble with that. It's not really that hard. If you have made changes to a file and you want to save them, you hit the colon key and you type, well, first to save changes, you would type W for write. We haven't given it a file name, so it has nothing to write to. But to quit and write changes, new colon WQ. Of course, it's not going to let me do that because I did not give it a file name. So in order to quit without making changes or saving changes, that's important if you get yourself in a situation like this where you did not provide a file name, then you would do colon Q for quit, and then exclamation mark, as if you're saying, you know, I told you to quit, and being emphatic about it. And that will allow you to quit the Vim text editor without making any changes. If we were to have provided a file name when we started, we can do Vim test file. It's already a file that we have created here. So I'll just go ahead and make some changes to it. It's not really important what's in this file. Right, and then we would do WQ, write and quit. And that would let us exit the file. We can actually see that that went into our file by using our cat command. We see our new changes down at the bottom. So that is a brief overview of the functions of less, more, and vim. Let's look at searching text using grep in Linux. Let's look at some basic ways to search for text. At times, you may have a large text file that contains a lot of data, and you might want to find specific information within it. For example, lines containing some particular text. One important Linux command that lets you search through text files is grep. So let's see how it works. The general syntax we will use with grep is grep, followed by the search options, then the search pattern file, and then the file. We can omit command line options, but we should specify a search pattern and a file we want to search through. For example, to search through the /etc/os-release file and find all lines that contain the text CentOS, we'd use this command. Search is case sensitive, so this command would show us different lines that would have this word with all the letters in lowercase. If we want to make the search case insensitive to find both CentOS with the capital letters and CentOS lowercase, or even CentOS in all capital letters, or any such variation, we can use the -I command line option. -I stands for ignore case. Instead of searching through a specific file, we can also search for all files that exist under a directory and its subdirectories. To do this, we add the -R option, and instead of specifying a path to a file, we specify the path to a directory. R stands for recursive. We can group recursive search with the ignore case option using -IR. Our regular user cannot read most of these files, so we get permission denied errors. If we want to search through system files that only the administrator account can access, we have to use sudo along with our grep command. So sudo grep -ir CentOS/etc would give us the following output. We can also invert search results. For example, we can search for lines that don't contain the text CentOS by adding the -v option. So that's for invert match. Now, consider this command. This matches both Red Hat and red. But what if we're only interested in matching the word red and not a bigger word that just contains the text red within it? We can use the -w option to match only words. And finally, notice how grep displays the entire line that has matched. This is useful as it shows us some context, showing us where these matched characters or words have been found. But sometimes, we'll only want to extract the results themselves, not caring about the rest of the line. We can tell grep to do this by passing the -o, or only matching option, to grep. Let's look at analyzing text using basic regular expressions in Linux. In our previous commands, we used simple search patterns looking for some specific pieces of text like CentOS. But what if we need more complex search conditions? So imagine we have some documentation scattered in hundreds of files, and we need to extract all IP addresses mentioned in these documents. And that would require more advanced search instructions. An IP has a form like 203.102.3.5. But we can't just make a search pattern look for numbers with a dot between them, as this would also match numbers like 1.2, which are not IP addresses. So in math, we can say something like x is an integer, and x is bigger than 3, and that x is smaller than 8. And this would mean that x is either 4, 5, 6, or 7. Regular expressions work in a similar way. We specify some conditions, tie all of them together, and our search pattern only matches what perfectly fits within those conditions. So let's start out with some super simple examples and then build up to slightly more advanced expressions. So all regular expressions are built with the help of operators like the caret, $sign, period, asterisk, plus sign, braces, the question mark, the vertical pipe, brackets, parentheses, and brackets with caret. So let's see what each one of them does. So here's a file with a set of names, and we need to find names that start with SAM. When we do a grep for Sam, we get names that start with Sam, but also names that have Sam anywhere in them. And that's not what we want. We just want the words that start with Sam and not those that have Sam in them. So that's where we use the line begins with operator. So this is usually the alternate character on the number 6 key on most keyboards. And using this operator within the search string only returns the lines that start with the given search term and not all lines that contain this term. And just to show another example, we could look for lines that start exactly with these 4 letters, PASS, like this. In the same example as before, we would like to only get the names that end with Sam. So for this, we would use the line ends with operator, which is a $sign. And we place this operator at the end of the search term to indicate interest to display only lines that end with a search term. So in this case, it would list the name Bassam. So here's some other examples. Say we need to list lines that end with the number 7. Using a simple grep with the number 7 lists multiple lines that contain this number. And we can tell our regex to look for a line that ends with 7 with an expression like this. That gives us a pretty clean result. So just like with the caret, with the $sign, we can look for lines that end with the sequence of characters. To look for all lines that end with the text male, do something like this. So please take note of how these operators are placed differently. If you mix up their location, you won't get any results, which can lead to confusion about why your regex is not working. So to easily remember their locations, think like this. The line begins with operator should be placed at the beginning of my search pattern, and the line ends with operator, the $sign, should go at the end of the pattern. So anywhere you add a period in your expression, it will match any character in that spot. So for example, C.T would match cat, cut, sit, caught, and even C1T or C$T, but it won't match CT. There must be exactly one random character between C and T. And with C period T, there have to be 2 characters. So an example would look like this, and we can see that even execute is a match because that sequence fits inside of that word. So if we'd only want to match the whole word with this and not parts of words, we can use grep's -W option. You can think of -W as word, and that would match only full instances of that and not partial word matches or words that contain it. And this brings us to an interesting problem. This period has a special meaning in regular expressions, but what if we need to search for an actual period in our text? Well, this won't work, as this regex will basically match each character one by one. So the solution, however, is simple. We look for a regular period by escaping the character. So escaping is how we tell our regular expression, hey, don't consider this period a match any one character operator. Instead, interpret it as a regular period. So to escape some special character, we just add a backslash before it. So instead of a period, we would write \period. So our grep command to search for a regular period to end a sentence, let's say, would look like this. So let's say that we have an expression like let asterisk. So this is going to match several things. It'll match le, but it's also going to match let, lett, lettt, and so on, no matter how many t's are at the end. So another way of saying this is that the asterisk allows the previous element, the t in this case, to be either omitted entirely, to appear once, or to appear multiple times. So in a grep command, we could use it like this. And we can see instances such as file, where it does not have the t appearing at all. And we can see instances, say, letter, where it appears more than once. So the asterisk operator can be paired up with other operators. So for example, to look for something for, say, sequences that begin with a /, have 0 or more characters in between, and end with another /, we could use a pattern like this. And since the period matches only any one character and asterisk says previous element can exist 0, 1, 2, or many more times, we basically allow any sequence of characters to exist between the /. And let's say we want to find all sequences of characters where 0 appears 1 or more times. So we might be tempted to use an expression like this, but as we can see, this also matches lines that contain no zeros at all. And why is that? That's because the asterisk lets the previous character exist 1 or more times, but also 0 times. It basically allows that element to be optional in our search. So we need another operator that forces the element to exist at least 1 time or many more. And the plus sign does this. So let's explore this a little more. 0+ would match strings like 0, 0, 0, 0, 0, 0, and so on. So we might think that we could write this in grep and find what we're looking for. But this doesn't look like the result we want. Our plus works like a literal plus sign instead of an operator. Why is this? That's because by default, grep uses basic regular expressions. The manual page for grep has this to say. In basic regular expressions, the meta characters $, plus, bracket, vertical pipe, parentheses, lose their special meaning. Instead, use the \/ versions or escaped versions. That means to use plus as an operator here, we have to add the \/ before it to make it \+, so our command becomes this. But this can be confusing pretty fast. We saw already that we use something like \period to turn the period operator into a regular period, and now we're using the \/ to turn a regular plus into the plus operator. So it'd be hard to keep track of what to \/ and what not to. So we can go the easier route and use extended regex instead, which doesn't require us to \ anything. And we can use the extended regex by adding the -E option to grep. Or even easier, we can use the command egrep. And we're going to look at grep and with the $E and egrep in our next video. So we can make it a habit to always use egrep instead of grep to avoid mistakes where we forget to \ one of our regex operators. Now let's build on our previous video on basic regular expressions and take a look at extended regular expressions that we can use in Linux. So we ended the last video talking about using the \ character or to turn the period operator into a regular period. So we also talked about using the \ to turn a regular plus sign into the plus operator. So we mentioned that we would use the -E option for grep or the even easier egrep. So let's take a look at those. Using the -E option so that we don't have to use the backslash escape character, we would have our 0 plus with plus as an operator look like this, or the equivalent egrep command would look like this. So it is a good habit to develop to always use egrep just in case you want to avoid those backslash characters and any mistakes that might come along with them. All right, so let's look at some more types of regex operators. Say we want to find all strings that contain at least 3 zeros. So we do this with brackets. Brackets say that the previous element can exist, or the contained element, I guess we could say, could exist this many times. So this would give you one where it matches 3 zeros at least. So to find all strings that contain a 1 followed by at most 3 zeros, we'd have an expression that looks like this. So note that this will also match 1s followed by no zeros. It's matching at most. And to find all strings that contain exactly 3 zeros, we'd have a construction that looks like this. So the brackets are the previous element can exist this many times. So a question mark will let the previous element exist precisely 0 or 1 times. It basically makes it optional. It can exist once or not at all. So let's say we're trying to find all text that says disabled or disable. So this means that the last D is optional. So we can write an expression like this with disabled question mark to use in grep. And I want you to note that this also matches the word disables. And this is a case where the letter D did not come at the end and disable still matches. Right, so we may have an expression like 0, and then our brackets, and we have a minimum value, a comma, and a maximum value. That's going to be used to find a match. 0 must exist at least the minimum number of times, and at most the maximum number of times. So to find all strings that contain 3, 4, or 5 zeros, we would write an expression which looks like this. And that way we can give a range of how many zeros we would like to find. So if we'd want to match enabled or disabled, we could use the vertical pipe, which is what we use to symbolize or, and construct a grep expression that looks like this. Basically matches what it finds on its left side or its right side. And we could combine this with a previous trick where we made the last letter D optional using the question mark to also find variations like enable or enabled or disable or disabled. And that grep expression would look like this. So a range is specified in the form of, for example, A to Z. So this will match any one lowercase letter from A, B, C, D, E, all the way to Z. We could do it numerically. Express a numeric range. 0 through 9 will match any one digit from 0 to 9. And sets are specified in a form like this. So this particular set would match any one character within A, B, Z, 9, 5, or 4. So say to find all strings that contain the text cat or cut, we could use a regular expression that looks like this. And that would leave either the A or the U inside the brackets to match cat or cut. So with ranges and sets, we can make our searches both wide and specific even at the same time. So for example, let's ask ourselves, how would we find all special device files which have names like /dev/sda1 or similar? Well, we could think like this. Find all strings that contain /dev/ followed by any random characters. So we might be tempted to write an expression like this with dot for a random character and an asterisk. This kind of matches some weird stuff because dot asterisk is really greedy. It matches way too many things after it captures what we're looking for. So we can make our search wide enough to catch all /dev devices, but specific enough to only capture the parts we need. And we're going to do that using ranges. So we can say after /dev/ match any number, that's going to be the asterisk, of lowercase characters from A to Z. We could use an expression which looks like this. So that looks a little bit better, but we can see that some things are still missed. /dev/twa is matched, but instead of the entire /dev/twa 0. So how can we catch the digits at the end too? Well, that's pretty easy. We specify that a digit from 0 to 9 should exist there, and we'd craft a grep expression like this. But now we run into another problem. Only things that have a digit at the end are matched with this new regex. We'll only find /dev/sda1, for example, but not /dev/sda. We're going to need to do a little more work. That's a pretty easy fix. We can just make the digit at the end optional with a question mark. So we could craft a regular expression like this, and that's starting to look much better now. So let's talk about sub-expressions. In math, we could see an expression like this, 1 plus 2 times 3, and we know that that's 1 plus 6, so that equals 7. That's because first multiplication will be done and then addition. But what if we first want to add 1 and 2 and then multiply by 3? Well, we'd write it this way in parentheses. And that way we know that this would evaluate to 3 times 3, which would be 9. So in regular expressions, we can do a very similar thing. So let's take a look at the last expression that we had used. So if we were to scroll up in the output, we'll see that we still don't match everything we need perfectly. We have, for example, /dev/tty0p0. The p0 is left out. So why is that? Well, that's because our expression, after it finds /dev, matches any number of A to Z characters and then a digit at the end. So that's it. That's where the match ends. So in /dev/tty0p0, after this first 0 is hit, our regex is happy with the partial result. So how could we correct this? So we could tell it that after /dev, we have some letters and a digit at the end, but after that, the same thing can repeat 0, 1, 2, 3, or many more times. So there can be other sequences of letters followed by a digit. So this way, /dev/tty0 would first match, and then p0 would be added to this match by that repetition. So we would basically want to say that this is part of this regular expression, and it should look for this pattern existing 0, 1, 2, 3, or however many more times, so it can match things like our tty0p0. So what makes regex look for an expression like tty0p0? And what makes it look for something to exist 0 or more times? So that's going to be the asterisk. But if we add the asterisk to the end, that's not going to be good. The asterisk would apply to the previous element only. And again, we want it to apply to our whole construct. So this is an easy solution. We just wrap the entire construct in parentheses, and this way the asterisk will apply to the entire sub-expression wrapped in the parenthesis instead of the last element only. It end up looking like this. So now we're going to get a match for our full expression /dev/tty0p0. But if we scroll up in our results list, we're going to find some things that still don't quite work. For instance, /dev/tty_s0 with the s0 not matching because we didn't include uppercase letters in the regular expression. So we could tell our expression to look for lowercase letters or uppercase with the vertical pipe operator. Okay? But writing it like this would be a mistake. And that's because the asterisk would only apply to the uppercase A to Z range, and we need it to apply to the entire expression for lowercase and uppercase letters. So once again, we can wrap our expression in parentheses to fix this. We end up with a little bit more complex but more precise expression that looks like this. And we can see that now our TTYS0 matches. And if we go on, we could look back and find other things that don't match, like this /deb/term/a, because our regex stops when it encounters the next slash, and so on. So this is the kind of logic and fine-tuning we would go through when fixing our regular expressions or making them laser-focused on what we need to find. So imagine we want to search for links to website addresses that don't use encryption. So this means that we would want to search for HTTP strings, but exclude HTTPS. So we saw how sets are in the form of, say, ABC123, and ranges take the form of A through Z. So if we add a caret in here, we can negate them. We can tell regex the elements in this set or range should not exist in this position. So we're going to use caret with brackets. So to look for HTTP links, we could have a regex that makes sure HTTP is not followed by the letter S. So it would look like this, and our regex would function this way. So in this case, we used a set with only one character, but we can use multiple if we want. For example, we could tell our pattern after a slash there should not be any lowercase letter. So we could use a set that looks like this. So keep in mind that for any pattern you're trying to match, there are multiple regex solutions you may find. To get this right, you should practice until you feel comfortable with regular expressions. And it's worth noting that regex is not limited to Grep. You can use regular expressions in a lot of programs that deal with search patterns. So for example, the sed utility also supports regular expressions. And you can find additional resources for regular expressions at this address. That's regxr.com.
So head over to the labs using the links given below and come back here once you are done.
Now let's look at how to create, delete, and modify local user accounts in Linux. Each person that needs to log in to our Linux server should have their own separate user account. This allows them to have personal files and directories protected by proper permissions. They also get to choose their own settings for whatever tools they use. And it also helps us as administrators. We can limit the privileges of each user to only what they require to do their job. This can sometimes reduce or prevent the damage when someone accidentally writes the wrong command, and it can help with the overall security of the system. It'll be up to us to manage these user accounts, which are sometimes simply called users. So let's dive right in and see how we create a new user on a Linux system. The command that lets us add a new user is intuitively called user add, and the simplest form we can use looks like this, where John can be replaced with whatever username we want to choose for this specific account. So after we run this command, the following things would happen. A new user called John is added to the system, and a new group also called John is automatically created. The group John will be set to be the primary group of the user John. A home directory is created for this account at /home/John. And this is where John can store his personal files and subdirectories, plus his program settings. Their default shell will be set to be the program found at /bin/bash. Whenever John logs in, this is the application he'll be dropped into. Effectively, his entire login session will run inside this app. And all the files from /skell will be copied to the user's home directory /home/John. And you can explore it with ls-a/etc/skell if you're curious to see what's inside. We'll see why this so-called skeleton directory is useful in one of the next lessons. And also, we need to note that the count will never expire. We'll see what this means later in this lesson. All of these things happen because the operating system is configured to take some default actions for each newly created account. We can explore these defaults with the following commands. a long form and a short form. Note the capital D for the short form. Other defaults related to account creation can be seen by exploring this file. The comments explain what each setting does. Okay, at this point we have an account for John, but how does he log in? His account has no password right now. To set a password for him, we can use this command. And if later we want to delete an account, such as John's account, we can use the userdel command. Note, however, that this will only delete the John user account. And also, the group with the same name John might get auto-removed, but John's home directory at /home/John will remain. And that's normal because his personal files might still be needed. But if we're certain that those files aren't necessary anymore, we can make the userdel command also remove the user's home directory and his or her mail spool using this command, and of course its equivalent short form. Now, coming back to our user add command, if we're not happy with the defaults, we could choose a different shell and a home directory with a command like this, or its short form on the second line. Of course, if we only want to choose a different shell but keep the default location for the home directory, we can just pass this option. These account details, such as usernames, user IDs, group IDs, preferred shells, home directories, etc., are stored in the file at etc password, and we can see them if we type cat etc password. So we'll see a line that looks like this. The first number, 1001, is the ID number associated with John's username. The next 1001 is the numeric ID of its primary group, also called John in this case. Then we can see the home directory and the preferred login shell. User add will automatically select a proper numeric ID from the available IDs, and it'll be incrementally done just by adding 1 to the last one. So for the first user, the ID will be 1000. For the next one, it'll be 1001, and so on. If we want to manually select a different ID, we can use a command like this, or its equivalent short form. The user Smith will have the numeric ID 1100, but also the group called Smith will get a numeric ID of 1100. If we want to see what username and group owns files or directories, we can do so with the usual ls-l. In this case, we'll use the home group, or home folder rather. But if we want to see the numeric IDs of the user and group owners, we can add the -n for numeric option, and they'll be shown to us. It might also be useful sometimes to find out more about the users we're currently logged in as. We can see the username we're logged in as, plus groups we're members of, alongside their respective IDs with the ID command. To print out just the username, you can type, "Who am I?" Up until now, we've created user accounts, but there's another type we can create called system accounts. To create a system account called sysacc, we just add the system option to user add. The numeric IDs of system accounts are also numbers smaller than 1000. So we might see an ID like 976 or 978 for our sysacc account. So why would we create these? User accounts are intended for people, and system accounts are intended for programs. So there will be no home directory created since it's not needed. And usually daemons use system accounts. We might see something like a database program running under a system account. Now let's remove these users and their personal files. If you're following along, these would be the commands that you would use to get rid of John and Smith. And if we ever forget the options for the user add command, we can get a quick reminder by using the help option. Now let's say we create the user John again. But later, we decide that we want to change some details for this account. The command usermod, or usermodify, that's what it stands for, is used for this purpose. So, for example, if we want to change John's home directory, we could use usermod with these options. The first line is the long version, and the second line that appeared is the short version. The move home option ensures that the old directory will be moved or renamed so that John can still access his old files. In our case, /home/John was renamed to /home/other directory. To change the username from John to Jane, we could use either of these commands, the long form or the short form. And to change a user's login shell, we could use either of these. An often used option with usermod is lock, or the equivalent short option with a capital L. This effectively disables the account, but without deleting it. The user will not be able to log in with his or her password anymore. However, they might still be able to log in with an SSH key if such a login method has been previously set up. To cancel this and unlock the account, we can use the unlock option, or its equivalent short form with a capital U. We can set a date at which a user's account expires. And to do that, we'd use a command that looks something like this. After expiration, they won't be able to log in and need to contact a system administrator to re-enable their account. If we want to immediately set an account as expired, we can just choose a date that is in the past. And the date format works like this. It's year, month, and then day. So to remove the expiration date, just specify an empty date. You'll use 2 quotes with nothing inside. We can also set an expiration date on the password. So please keep in mind that this is not the same as account expiration. Account expiration completely disables user logins. Password expiration forces the user to change their password the next time they log in. They can still use the account. So if we want to immediately set the password as expired, we can use this command. And change stands for change age. So we would just set the last day to 0 for Jane's account. Next time Jane logs in, she'll have to change her password. If we want to cancel this, we can unexpire the password by passing -1. And if we want to make sure that a user changes their password once every 30 days, we could use the max days option and pass the parameter for 30. So if we want to make sure their password never expires, we can set max days to -1. And to see when the account password expires, we can use the list option to see that information. In case you followed along with this exercise, you want to delete the user called Jane and the group called John, and you can do so with these commands. If you haven't done so already, don't forget to subscribe to our channel. Now, let's explore how to create, delete, and modify local groups and group memberships in Linux. Each user can belong to one or more groups. And why are these useful? Well, here are a few examples. We have a directory full of files that our developers need to work on, so they all need read and write permissions. We'd have to allow 3 user accounts to edit these files: John, Jack, and Jane. An elegant solution to this problem is to create a new group called developers. Then we add our 3 users to the developers group, and finally we make the developers group the owner of those files. And we change permissions so that the developers group can read and write to them. Now, John, being part of the developers group, can easily edit those files. And if we want to temporarily deny John access, we just remove him from the developers group. Or if a new member joins our team, we can just add their user account to the developers group and boom, they have read and write access to those files. We can see how this makes things easier to understand from an administrator's perspective. It's like assigning roles to user accounts, or like user accounts have a label: is a developer or is not a developer. All of this by simply deciding if they will be part of the developers group or not a part of that group. And speaking of roles for user accounts, groups can have other special effects. For example, being part of some group can grant special privileges on the system. Two common examples. One is the users in the wheel or sudo group who are allowed to do pretty much anything on the system. They can run any program with root privileges, with root being the most powerful user account in Linux. Another would be users in the Docker group who can manage Docker containers. We said that a user can belong to multiple groups, but one of these groups is special. One of them is the primary group, while all of the others are secondary or supplementary groups. The primary group is also called a login group. That's because as soon as the user logs in, this becomes his or her main group. But it's hard to understand with theory alone, so let's see what's so special about this primary group. Here are two practical examples. When a user launches a program, it is said that it runs under that user account and group. Otherwise said, the program runs with the same privileges that the user account and its primary group have. And here's another, perhaps more visible example. When a user creates a file, this file will automatically be owned by the user account and their primary or login group. If you want to follow along with this exercise, you'll need a user called John beforehand. You can create one using the user add command. And it's easy enough to create a new group called developers with a command like this using group add. But how do we add our user John to this group? The easiest way to add a user to a group is with the help of the gpassword command. This name comes from the words group password, but don't let the name fool you. Nowadays, group passwords are almost never used in practice. So the main use case for the gpassword utility is to add or remove users from certain groups. And to add users, we can use this gpassword command or its equivalent short form command. And if we want to confirm that this has worked, we can see the groups that John belongs to using the groups command. So in this output, the first group after the colon is the primary or login group, and anything else that follows that are the secondary or supplementary groups. And if we want to remove a user from a group, we can use the delete option or the corresponding /d short option. On rare occasions, we might want to change the user's primary or login group, which is the group that was automatically created with the user account and has the same name as the user. And we can do that with a command like this using usermod-g. And a user can be part of multiple groups. Secondary groups are created separately from user accounts, and a user can only have one primary group. We can have many secondary groups. So while we're working with usermod, it's important not to confuse this lowercase g with the capital G, as the capital G option changes the secondary groups and not the primary one. So to avoid this mistake, we can make a habit to use the equivalent long option, --gid, instead of -lowercase g. So now if we take a look at John's groups, he's only a member of the developers group, and that shows that his primary group has changed. I'd also like you to note a difference here. gpassword first expects the username and then the group, but usermod has a reverse order of group name and then the username. And if you find yourself needing help and a refresher on this, you can always use gpassword --help to take a look at these options, and that will show the corresponding syntax showing that the username must come first when using gpassword. Now to rename the group called developers to programmers, we could use a group mod command like this, give it the new name option, or we could use the equivalent short form command, which is -n. If we want to delete a group, we have the group del command. And if we try to run that, we're going to see an error if it's someone's primary group. Say group del cannot remove the primary group of user John, for example. So to fix this, we can change John's primary group back to the John group with this usermod command, and now we can finally delete the programmer's group. So if a user is part of a secondary group and we want to delete it, the command will work without any issues. There's no need to first remove the user from that group before deleting it.
So head over to the labs using the links given below and come back here once you are done.
Now, let's look at managing user resource limits in Linux. When we have a lot of users logging into the system, we may want to impose limits on what resources they can use. This way, we can ensure that user A does not use 80% of the CPU, leaving very little to spare for the others. To set such a limit, we can edit this file. We can see as we look through it that it's a well-documented file. We'll want to move down until we see this. So we can see that the syntax for setting a limit is domain, type, item, and then value. So let's break this down into easy to understand parts. First, the domain. What can we specify here? Usually it's one of these three things. One is the username. In this case, we can just simply type the name of the user, such as Trinity. We can use a group name. To set a limit for everyone in the developers group, we just add an @ symbol in front of its name, so we'd write @developers to get such a group limit. And the next thing that we can use is an asterisk, which will match everything. Setting a limit for asterisk basically says set this limit for every user on the system. So it's a way to set a default limit. Why default? Because this limit will only apply to every user that is not mentioned in this list. A user limit overrides an asterisk limit. So, for example, one asterisk limit can specify that everyone can only launch 10 processes, but then another limit for the user Trinity says she can launch 20 processes. In this case, the limit for everyone will be 10, that's the default, but for Trinity, it will be set at 20. Next is the type, which can be three different values: hard, soft, and dash. A hard limit cannot be overridden by a regular user. If a hard limit says they can only run 30 processes, they cannot go above that. So it's basically the top, the maximum value for a resource someone can use. So to set a hard limit, just specify it there in the second field. A soft limit, on the other hand, is different. Instead of a max value, this is more like the startup limit, the initial value for the limit when the user logs in. If a user has a soft limit of 10 maximum processes and a hard limit of 20, the following happens. When they log in, the limit will be set to 10 processes. But if the user has some temporary need to increase this, they can raise it to 11, 12, 15, or even 20 processes. This way, they can get a slight increase when absolutely required, so they can manually raise it to anything they require, but never above the hard limit. And last, we have the dash sign. This specifies that this is both a hard limit and a soft limit. With this, we're saying our Trinity should be able to run 20 processes at the most. When she logs in, she should be able to use up to her entire allocation without needing to manually raise her limit. Next up is the item value. This decides what this limit is for. We can have things such as nproc. And nproc sets the maximum number of processes that can be open in a user session. We could have fsize, which sets the maximum file size that can be created in this user session. The size is in kilobytes, so 1024 here means the maximum file size is 1024 kilobytes, which is exactly 1 megabyte. We can also use CPU, and CPU sets the limit for CPU time. This is specified in minutes, so when a process uses 100% of a CPU core for 1 second, it will use up 1 second of its allocated time. If it uses 50% of one core for 1 second, it will use up 0.5 seconds of its allocation. Even if a process was open 3 hours ago, it might have only used 2 seconds of CPU time. If you want to see more stuff that can be limited, just consult the user manual for this limits.conf file using the man command. Now let's test our knowledge and add a limit for our user called Trinity to ensure that she can open a maximum number of 3 processes. So first we'd find this line in the file. And to do that, we would add a line that looks like this. We want to make sure there's no pound sign or hash sign, number sign, whatever you would like to call that, comment sign at the beginning of this line. The Vim editor might automatically add it when you press enter to add a new line here. So make sure to delete the preceding pound sign. Otherwise, the line would be commented and have no effect. Now, let's save our file and exit. To log in as Trinity, we can enter this command. I instructs sudo to do a real login, and U specifies the user we want to log in as. So at this moment, only one process is permanently running in her session, the bash shell. So we should be able to run 2 more processes. Let's launch PS and pipe the output to the less pager. We can see it works, and now it got us to running 3 processes, the maximum limit. Now, what would happen if we'd tried to launch the 4th process? So let's press Q to quit the less pager and then try the following. This would try to launch 3 new processes, ls, grep, and less, plus bash already running, which would total 4 processes. And we'll see this failing as expected. We cannot run more than 3 processes. So let's type log out to exit from Trinity session. So if we want to see the limits for our current session, we can type ulimit-a. We have small hints between parentheses. For example, we can see -u displayed for max user processes. This means that we could type ulimit-u 5000 to set our limit to 5000 processes. By default, a user can only lower his limits, not raise them. The exception is when there are hard and soft limits. In that case, the user can raise his or her limit all the way up to the hard value, but only once. After the limit is raised with a ulimit command, the next command can only lower it. It cannot be raised the second time, even if the hard limit would allow it. Now, let's examine how to manage user privileges in Linux. Every time we had to make some important changes to the system, we used sudo in our commands. That's because only the root user, also called super user, can make changes to important areas of the operating system. Whenever we put sudo in front of a command, that command runs as if the root user executed it. So how come our user is allowed to use sudo? If we type the groups command, we'll see our user is part of the wheel group. Whoever is part of this group is automatically allowed to use sudo. This means that the easiest way to give another user sudo privileges is to add them to the wheel group. To add our user Trinity to the wheel group, use a command like this. And that's it. Now this user can get administrator privileges whenever they want. But this gives them power to do anything they want on our system. What if we want a more fine-tuned control? Then we could take a different approach. There's a special file at etc sudoers that defines who can use sudo and under what conditions, what commands they can run, and so on. But we should not edit this file directly. We use a utility called vsudo. This utility can check if our edits are correct to help us avoid mistakes in the file. So first, let's remove Trinity from the wheel group to make sure she can't use sudo anymore, and instead define a different sudo policy for her later. We can remove her with this command. And then to start editing the etc sudoers file, we use sudo vsudo. And this opens in the Vim editor. The file is thoroughly commented, but we're not interested in the first few parts, so let's navigate to the end, and we'll notice this line. Now, we see why any user added to the wheel group can run any command with sudo. So let's break down this line into 4 different parts and analyze what they do. The first is the user or group. Here we define who this policy is for. The second is the host. Here we could specify that these rules only apply if our server's host name or IP address has a specific value. Not useful for our purposes, so we'll just type all for this host field. The third is the run as field. Here we could type a list of usernames. Normally, sudo ls would run the ls command as root, because that's what sudo does. It runs the command after it as a different user. But sudo can also be used so that Aaron can run commands as Jane or vice versa. We'll see more about this later. So if we list Aaron, Jane in this run as field, then sudo can only be used to run commands as the user Aaron or Jane, but not root. And finally, the fourth field is the list of commands that can be executed with sudo. So we could say the syntax for policy defined in the sudoers file looks like this. Now, let's go through some examples. To define a policy for our Trinity user and let her run any sudo command, we would need to add a line that looks like this. To specify a policy for all users in the developers group, we would add a line like this. We mentioned sudo lets us run commands as root, but also as non-root regular users. So, for example, to run the ls home Trinity command as the user called Trinity, we could write this as a command. After the -u, we specify the username we want to run as. So, if this third field is all, then this policy allows someone to run sudo commands as any user. But if we'd want to have Trinity to only be able to run sudo commands as the users Aaron or John, we could write a line like this. Also, note that this is wrapped in parentheses, which hints to us that the field is optional. So a line like this is also valid. And we mentioned that in the fourth field, we can specify a list of commands. With our previous entries, the user or group granted sudo privileges could execute any command, but we could limit them like this. Now, Trinity could only run commands such as sudo ls or sudo stat bin. Only ls and stat commands would work. If Trinity tries a command like this, she would get an error. And since we specify the third field as optional, this line could also be written to look like this. We know that the first time we run a sudo command in a session, it asks for our current user's password. In our sudoers file, we see a hint above how we could get rid of this requirement. So we could use the example in the comments, which looks like this, and figure out how to apply this for our user Trinity. If we want her to be able to run sudo commands without providing her password, we could write this line in the sudoers file.
So head over to the labs using the links given below and come back here once you are done.
Now, let's examine how to manage access to the root account in Linux. We already saw one method to temporarily become root whenever needed. When we run a command, such as this, using sudo, it's basically the same as if the root user would have executed that command. But what if we want to log in as root? For a user with sudo access, we can enter this command, or its equivalent short form command. And that's it. We're logged in as root. To exit from root session, we'll type logout. If the user does not have sudo privileges but knows root's password, they can use su- or su-l or the long form with --login. All of these commands do the same thing. They log you in as root. Some systems might have the root account locked. This does not mean that we can't use the root user, it just means that we can't do a regular login with a password. When root is locked, we can still use sudo login to log in as root, but we can't use su-, as that would ask us for root's password, which is currently locked. If we want to allow people to log in as root with a password, we have two options. If root never had a password set, we could just choose a new password for it. Or if root had a password set in the past, but then the account was locked for some reason, We can unlock it using either the long or short form of the password unlock command. And after using one of those steps, then we can use su- and type the password for root to log in. Of course, we could find ourselves in the reverse scenario. Imagine this. Currently, people can log in as root. We figure that this is a bit insecure. And so we can lock password-based logins to the root account with the lock function of the password command. Either the long or the short version would do the same thing. So other logins might still be possible if they were previously set up. For example, if an administrator has set up logins via an SSH private key, they'll still be able to log in even if the root account is locked. Make sure to only lock root if your user can use sudo commands. With no root login and no sudo, you'll find yourself in the situation of not being able to become root at all, effectively locking yourself out, not able to change important system settings anymore.
So here we are at the end of this Linux crash course. I hope you enjoyed the material and gained experience with the labs. We've covered the basics of Linux, but there's a lot more. There's more to learn about networking, service configuration, storage management, troubleshooting, monitoring, process management, and so much more, like virtualization, for example. All of these are covered in the Linux Learning Path. So this covers 3 certification courses: the Linux Foundation Certified Systems Administrator, the LPIC 1 series, and the Red Hat Certified Systems Administrator course. Don't forget to subscribe to our channel as we release new videos about Cloud Native and Kubernetes all of the time. Until next time, goodbye.